In this video, I'm going to go over a one-sample z-test for proportion. We're going to use the 4C inference method. As you can see, I have the template here for us to look at, and we'll go through that as we answer this question. So CNN once claimed that half of teenagers are addicted to their phones. So that's the claim. A random sample of 180 teenagers was selected, and 72 reported they are addicted to their phones. Is there convincing statistical evidence that the proportion of all teenagers who are addicted to their phone differs from 0.5, using alpha of 0.05? Okay, so this information gives us a lot. First, the procedure. I have a single proportion that I'm comparing to a claim, and that is 0.5. So this is a one sample z-test for a proportion. Our proportion is the statistic. P hat tells us that 72 out of 180 said they are addicted to their phone. The parameter is what we see here, convincing evidence of the proportion of all teenagers who are addicted to their phones. So the true proportion a little. So we're trying to estimate or see if the true proportion of all teenagers who are addicted to their phone differs from 0.5. So our hypotheses, our null hypothesis, will be that P is equal to 0.5. The claim of half of teenagers being addicted to their phone. Our alternative is going to be the not equal to, because it just says differs. It doesn't say it's greater than 0.5, doesn't say less than 0.5. If the question is saying is different from, we use not equal to. And what is our evidence? Well, our evidence is that 72 over 80 is 0.4, right? So 0.4 is less than 0.5. So our sample is less than what is stated. So there's a little bit of evidence for HA, but is that convincing evidence? So we're going to check our appropriate conditions. The conditions are the same that they've been for the last several tests that we are doing. The first thing is always randomness. So it says a random sample of 180 teenagers. So our first condition, random sample of 180 teens. Why? So we can generalize. And 180, we're sampling without replacement, so 180 is less than 10% of all teenagers. So we can sample without replacement. And then our large counts, we check NP and NQ. And when we do that, we check it against our hypothesis. If our hypothesis is true, we would expect 180 times 0.5 successes, which equals 90, greater than or equal to 10. And then 180 times 0.5, because 1 minus 0.5 is 0.5, 90 failures. Remember, this is called the success failure condition. We need more than 10 successes and failures. And if that were true, this is what we would expect. So we can use a normal model. Okay, so our conditions are all met. Perform the calculations. The general formula is our Z is equal to the statistic minus the parameter divided by the standard deviation. In this case, our specific formula is the z-score is p hat minus p naught. That's the hypothesized value, divided by the square root of p naught Q naught, or we can write 1 minus P naught over N. And we'll plug in our numbers. Our proportion from the top there was 0.4. So P hat is 0.4 minus the hypothesis of 0.5 divided by the square root of 0.5 times 0.5 divided by 180. And we plug this into our calculator. I like to get my standard deviation first. And so this is negative 0.1 divided by 0.037. And I get negative 2.703. That is my test statistic. The z-score is my test statistic. And we're going to draw a quick picture of what's going on here. We have 0.5, and my standard deviation is 0.03. So 0.463 and 0.426. and 0.389. And I'm only going to draw this part because my P hat is right here in between the 0.38 and the 0.42. So that's the area that we're trying to find. Once we have our test statistic, we find that area by using normal CDF. Now, since this is a not equal to hypothesis, it's two-sided. So two-tailed means we're going to multiply the p-value by 2 once we find it. And then how do we determine whether we're going to use negative 99, comma our z-score, or our z-score, comma 99? With the not equal to test, it doesn't tell us which direction. Greater than, we would use positive 99. Less than, we would use negative 99. But the not equal to depends on the sign of our test statistic. So because our test statistic is negative, and I want to find this area, I also, because it's two-tailed, am interested in the same area on the other side. That's what I'm going to multiply by 2 to find the sum of those two areas. And it's symmetrical. So it's normal CDF, negative 99, negative 2.703, and then we leave the 0 and 1 in there. So negative 99, negative 2.703 gives me 0.00344. And then we're going to multiply that by 2. And our final p-value is 0.00687. Okay, so that's my p-value. My p-value is the probability of getting our sample, 72 out of 180, if the true proportion of teenagers addicted to their phone is 50%. Now we make our conclusion. We do 2 things for our conclusion. We first interpret your p-value. And that is assuming the null hypothesis is true. P equals 0.5. There is a p-value chance, so my p-value is 0.00687 chance of getting our sample p hat equals 0.4 or more extreme purely by chance. And then we do our conclusion. It's this part, because 0.00687 is less than the alpha of 0.05. If our alpha is less than if our p-value is less than our alpha, then we are rejecting. The evidence is so unlikely that this was actually by chance that we don't believe the hypothesis is true. So we reject HO. There is convincing evidence that the proportion of teenagers addicted to their phones and the best way to state this is really to repeat what's in the question. And if we go back and look at it, it says, where is it there? Differs from 0.5. If you just take this whole part in your conclusion and use that, that's the best way to make sure you've covered your context correctly. So addicted to their phones differs from 0.5. And that's our conclusion. That is your quick one sample T test.